Can I share my screen?
Yep. Yeah, you should be able to do that now. So our next speaker is Hasti Nateghi, and she's going to tell us about the CGM.
Thank you. So I assume you can hear me. And hello, everyone. My name is Hasti, and I'm a PhD candidate at CAS, Swinburne University, working with Glenn Capsock and Nikki Nelson. And you can see our other collaborators here. Today, I'm going to talk about the kinematic connection between galaxy and CGM. And circumgalactic medium, or CGM, is a multi-phase reservoir of gas that resides between interstellar and intergalactic medium. Our current picture of CGM shows that the gas accretion aligned cosmic filaments provide fuel for galaxy star formation and adds angular momentum to the disk, and stellar winds and supernovae feedback will be ejected through the outflows. And this outflowing gas can recycle back to the galaxy. These features all make the CGM a great laboratory to study the baryon cycle of galaxies. Quasar absorption line technique is the best method to study the CGM. In this technique, the light of a bright background quasar passes through the CGM of a foreground galaxy, and the spectrum of this quasar can provide us with the gas information like abundances or kinematics. In order to address how the baryons cycle in and out of galaxies, we use the kinematics. We connect the kinematics of CGM, or circumgalactic medium, to the host galaxy disk, looking for evidence of gas accretion or outflows that could directly affect the galaxy's star formation rate. From simulations perspective, the flows of gas through the CGM can regulate the growth of the central galaxy. Simulations expect the metal-enriched outflows with high radial outward velocities existing along the galaxy's minor axis, and in contrast, gas accretion with velocities toward the central galaxy along the galaxy's major axis or along the disk. Furthermore, observations also imply that the halo gas is not isotropically distributed around the galaxies. Using a sample of magnesium to absorption, Capsock et al. Showed that there is a bimodality in the distribution of CGM around the galaxy, where most of the gas can be found along the major and minor axis, where we expect to see accretion and outflows. Simulations also depict the accretion of cold gas onto the galaxies. Using cosmological simulations, Stuart et al. Showed that the cold gas enters the halo of galaxy preferentially along the direction of cosmic filaments with high angular momentum. This filamentary accretion can occur as an extended disk-like structure rotating roughly in the same direction of galaxies. Simulations also show that the best way to trace this gas accretion is when the CGM has line-of-sight velocities consistent to the host galaxy. Observations of cold outflows in the halo of M82 shows that the rotation velocity of the gas declines as a function of height from the galaxy disk. This figure shows the mean rotation velocity of the disk as a function of offset along the major axis, and different colors represent the measured velocity in different cuts parallel to the disk but above and below the galaxy plane. And we can see here that the rotation is more visible in the cuts closer to the disk, but it decreases as a function of height. So based on these sort of observations, we don't expect to see rotation in the outflows, especially at large distances. As I already mentioned, simulations predict that the gas flows are critical for galaxies' growth. Although there's a few observational evidence for gas accretion, simulations expect that the CGM gas flows should be detected in the form of high column density neutral hydrogen, as we can see here in this figure. Here we can see that the H1 gas with column densities mainly between 10 to the 16 to 10 to the 19 flowing in and out of galaxies. In this project, we also use H1. We use H1 to examine how the CGM and galaxies are related and whether this relation is dependent on the H1 column density or not. And why we're interested in H1? CGM is a multi-phase environment comprised of low and high ionization phases of gas with different temperature and different density that can be also traced with different ions like magnesium 2 and oxygen 6. But H1 is the best tracer for the full range of dynamical processes in the CGM because H1 can trace cold, cool, and warm CGM and can be found along different quasar sightlines. To statistically address how the CGM and the galaxy are kinematically connected, we used 70 sightlines with H1 absorption detected in the CGM. And the Keck ESI provided us with the galaxy spectra, and using the high resolution galaxy spectra, we extracted the rotation curve of galaxies. The HST COS spectra of background quasar in each field provided us with the gas information like kinematics and column density of the H1. And the HST imaging of the field is used to measure the orientation of galaxies like inclination and azimuthal angle. We also modeled the halo of galaxies, the CGM, to compute the maximum velocity of the halo along the quasar sightlines using a monolithic rotating thickness model from a Stadel. And to examine whether the absorption can be explained with accretion or a corrotation, we calculate the equivalence with corrotation fraction of gas. So we compare the kinematics of galaxy with the absorption to see whether the bulk of absorption is aligned with the galaxy's systemic velocity where the quasar sightline penetrate the halo. For example, in this system, the bulk of absorption is aligned with the left side of galaxy systemic velocity where the quasar intersect the halo. And if we measure the equivalence with corrotation fraction, we see that 64% of the gas has consistent kinematics and most probably corrotating with the galaxy. So we examine the corrotation fraction of H1 as a function of different parameters like column density, projected distance from the galaxy or impact parameter, and halo mass. H1 can be found over a wide range of column densities, and it seems that the lower column density H1 coming from the IGM and higher column density H1 greater than 14.5, most probably related to the CGM and the galaxy itself. Here we have plotted the equivalence with corrotation fraction as a function of H1 column density or absorption strength. And individual data points here, the gray points are the individual systems and the purple points are the average corrotation fraction in beams of column density. Here we can see that the fraction of gas that is corrotating with galaxy increases with increasing H1 column density. So the stronger absorbers, either associated with accretion or outflows, are most likely coupled to the host galaxy. This is consistent with simulations where they predict the gas flows are mostly associated with the strong H1 absorbers. So we already know from simulations that the CGM gas flows are consistent with column densities greater than 10 to the 16. To test this, we plot the equivalence with corrotation fraction as a function of virial radius normalized impact parameter, and we split the sample into two weak and strong absorbers at column density of 10 to the 16.2. And here we can see that the corrotation fraction of weak absorbers highlighted with pink decreases with increasing distance, but the corrotation fraction of strong absorbers highlighted with purple increases with increasing distance. So this shows that the stronger absorber with column densities greater than 16.2 are likely corrotating with the host galaxy. But does this strong absorber with signature of corrotation trace the accretion? Actually, we don't know, because in these two plots that I already showed, we have gas in different locations around the galaxy. So to answer this question, we need to know how does the corrotation change with azimuthal angle? This plot shows the corrotation fraction as a function of distance and azimuthal angle. So here, the galaxies are centered at 0 impact parameter, and their major axes are aligned with the azimuthal angle 0. And these data points are the H1 gas detected in the background quasar sightline, and they are color-coded with their equivalence with correlation fraction. And surprisingly, we find high correlation fraction along both major and minor axes of galaxies. So this could show that the gas with high correlation fraction along the major axis could probably trace the gas accretion onto the galaxy, but the correlating gas along the minor axis may trace the outflows that are still kinematically coupled to the host galaxy where they are ejected from, or this could also trace the galactic fountain where the gas recycled back to the galaxy. This is inconsistent with previous observations where they couldn't find the corrotation or signature of rotation in the outflows. Also, our findings are in contrast with simulations where they predict a suppression of H1 gas in the halo of massive galaxies. Here we have plotted equivalent correlation fraction as a function of halo mass, and here clearly we see there are 17 systems with H1 absorption detected in their CGM, and they have halo masses greater than 10 to the 12. This is in contrast with simulations where they show that the H1 covering fraction drastically drops down in halo masses greater than 10 to the 12. So if you are interested in more results and more detailed analysis, please stay tuned for my paper later this year. And I leave you with my summary. Thank you so much.
Questions? John,
I go up to the mic.
yeah, I thought we did.
Hi, Hasti, this is really good work. I have a question for you about the H1. So you said you got the H1 from cost spectra. Was it Lyman alpha alone, or was it the Lyman series? I'm wondering how well the H1 was actually constrained by the cost spectra.
Actually, that's a good question. Our sample, is I can say it's comprised of two subsets. Why the one subset is mainly IgM gas, so low column density H1. That in that system we can constrain the column density. So just using Lyman alpha because the absorption line are not saturated. So in that systems we only have mainly Lyman alpha, but in the systems that we have CGM gas, so mainly they're saturated, we have also Lyman beta and in some cases Lyman alpha, and that is how we constrain the column density of the gas.
There was a question on Zoom, which is, do you see any evidence of counter rotation? If so, what is its relative fraction?
So actually by counter rotation, if you refer to the counter rotation and this phrase, for example, from the previous works that they have used, so we say this amount of gas is consistent with co-rotation. But if we want to, say this gas or this system is counter rotating, I think it's a strong word, because if this is a gas, a system is not co-rotating, we cannot say for sure it is counter rotating. It may not be consistent, it might have higher velocities. So that's why we don't use this phrase counter rotation. But if we want to use this counter rotation, yeah, we have also counted the systems. So if the systems have velocities within the model, within the statal model prediction, we call them co-rotating, following the older methods. And if they are not within the statal model prediction for the halo, we call them counter rotation. So I haven't showed those results in my slides, but you can see them in my paper later this year.
All right, great. Other question. I have one quick question, which is how do you determine your sample of galaxies?
How we determine the sample of galaxies? So actually this is basically half of this big sample is part of our big survey, multi-phase galaxy halo survey. So we had at first we had a rough SDSS photometry redshift of galaxies. We searched for the CGM or the background quasar. So if we were successful to find a background quasar, so that system was approved. So then we requested the time to take the galaxies, spectrum, because we were sure that we have CGM detected around these galaxies, and we had CASA spectra of those quasars, but the almost half, 40 systems are from multi-phase galaxy helio survey, and 30 is collected from literature. So we look for galaxies with both CGM properties and rotation curve measured in literature. So that is how we collected the sample. I'm not sure if I answered your question.
Yeah, that was great. Thank you.
No worries.
All right, so I think we can move on to the next speaker. Let's thank our speaker again.